Hi everybody, I'm Dimitri Geskus from Chilas. I'm CTO of Chilas, so I know all the technical details, at least people think I do. And I looked at the audience there and I've got one question for you, and the chat is about what is your laser you're currently using or light bulb you're using for your application. And then after this presentation, I will be curious of what your requirements are for a laser source and how we can strengthen each other's business. So I think that's the thing. Today I will tailor a little bit to the medical applications. And what I also saw in the audience that there's a lot of integrators there and people from other fields there. So I will also have some other applications there. In the presentation, I will go through the history of Chilas, as I show over here, then the technology involved, the product line. I have some little bit of a demo there, some video footage, and then some applications at the end. Feel free to interrupt me if you have any questions, but also questions can be asked later via the chat or after this meeting. Well, a little bit of myself. I did a lot of photonics, lasers related stuff. And since 2011, we made the first hybrid laser. And at that time, it was in some of the now agglomerated companies of Linux International. At that time, there was no real business for it, but it was at least a fancy thing to show that we can make lasers on a photonic platform by hybrid integration. It took a few years and prophecy to the outside world to convince everybody to use these light sources and use photonic chips for all kinds of applications. And here the laser that Chilas is currently putting onto the market is one of the most simple hybrid integrated devices, in my opinion, you can make. It's two chips, a gain section, and a feedback circuit and a fiber to the outside. And you've got a unique laser which is very compact and gives a lot of new things to dream about. 2018, Chilas was founded, and 2020, we had the first product launch, which was a 50/50 laser. And from 2024, so 2 years ago, we really have a module on the market where you don't have to think anymore about the technology inside. It's just a hybrid laser module. So you just plug it in, run the software, and toggle the switch. We've got some distributors all across the world, and the supply chain of chips and assembly is all there, and the assembly is nowadays fully automatically. So this is a little bit of how it looks like. 2019, small packages. We send these things abroad. People giving some instructions, a lot of support there to tell them how to drive the lasers. Then in 2020, we had the laser driver, which came with a graphical user interface, so people could do some basic functions there, where the chip sits nicely in a ZIF socket, so you can replace it and people can learn how to work with the laser, but not really a product to a level. Since 2024, we've got these nice modules where all the electronics is integrated there. There is a user interface, there is analog inputs, etc. to lock the laser, to tune the laser, and you actually don't have to think anymore about what the technology is inside. You just replace your current laser source with a Chilas laser. That's the goal. Well, how does a laser work? I think it's important to know a little bit about the mechanics behind it. For a laser, you need basically two building blocks. One is a gain medium that generates the photons, and we have the block over here. It's a semiconducting optical amplifier, and you need a resonator, a feedback circuit, and we use here a small circuitry which is in the form of a silicon nitride feedback circuit. You look at the feedback circuit, you see these two rings. These are two ring resonators. And if you look at the optical performance of response of a ring resonator, you basically get a frequency comp or a wavelength comp being transmitted from this bar all the way to the output bar. In the top graph, you see the response of such a ring. So the green response curve responds to the of the first ring, and the blue response curve of the second ring. Now you directly see that the response lines seldomly overlap. Only once in so many times they do overlap, like a vignette. And when they overlap, light can travel from this wavelength all the way back to that wavelength, back into the cavity. And the laser locks to that wavelength because no matter which direction you go there, that color of light will be feed back into the amplifier and will be amplified. Thereby I get intensity buildup, which is much higher than all the other side lobes of the feedback circuit, and you've got a very nice laser. Now, a laser is very boring if you can't tune it, in my opinion. So we put some heater elements on that, and we can change the refractive index very fastly, and we can shift the frequency comp of one of the rings with respect to the other rings. That's new to me. This should work then. Okay. When one of these frequency comps is shifting, you will see that the laser can hop over the ring responses of the non-tuned elements. But technologists inside in this call is there. So we've got 2 pi phase shift. That means that we can shift a full free spectral range with respect to the other ring. So we can hit virtually any wavelength there is, as long as the gain section allows us to have a laser oscillation on that. Now lasers, the longer the cavity is, the narrower the line width. So if you have a DFB laser, the cavity is very small, the line width is typically expressed in some nanometers. But if you have a very good feedback circuit, long cavities, high Q, then you get very narrow line width. And we don't speak anymore about wavelengths, but we speak about kilohertzes or megahertzes line width. And if you do the calculations from wavelength to frequency, then you get to these frequencies there. So very narrow line width because the cavity is elongated into a passive material. And thanks to the vignette, we get a very broad wavelength. Based on this principle, we developed some electronics, and the most important development of the last 3 to 5 years is the electronics development. Remember, there are some free heaters to tune, and most of the physicists, so this heater to tune to your favorite wavelength, and most physicists cannot count further than 3. 1, 2, 3, many. And it's a bit tricky to tune the laser to your favorite wavelength. So we calibrate the lasers in our labs, and we make lookup tables there. So you get in the graphic user interface a slider to select your favorite wavelength, and the laser sets itself directly to that wavelength. In that branch, we've got the Atlas, which is a wavelength selectable laser. We've got a Comet, which is a swept source, where we stitch all the wavelengths nicely together, and we get a swept source application for swept source applications there. And we've got a special new thing, which is a Polaris, which is a stabilized laser only for a single wavelength there. So start with the boring laser. Well, not too boring, I must say. This laser is a stabilized laser. You order this laser by a wavelength in the ITU grid. Well, most of the biomedical applications are not in the telecom range, but it shows you at least capability of the platform. And since we are not needing to tune the laser phase noise is super, super low. These lasers find their way into quantum applications where they want to tickle some atoms into an atom clock, or some quantum key distribution, or some vibration sensing like dark fiber sensing or other sensing applications there. Mostly for telecom industry or for quantum applications there. I think for this talk, I think the Atlas is by far the most interesting laser we have here. We can replace the gain section with several other wavelengths. So we've got wavelengths now emitting around 685 with 10 nanometer tuning range, 850 with around 40 nanometers tuning range, and then the telecom wavelengths, which are the working horses for Chilas, which are around 1550, so C band, well, SCL band for telecom, 100 nanometer tuning range, 1590 and 1700, the U band lasers there, and they all rely on the same piece of electronics and the same interfacing there. Here's an example of, for example, the Atlas 1550. So it can tune from 1550 all the way to 1600 nanometers. And you've got a very nice suppression ratio over 45 dBs. And you get a very nice no phase noise graph there. All these lasers have an analog input, so you can lock to some applications. If you have a transition you want to monitor, you can electronically lock and brief the mode with a very fast way to follow some features you want to follow. Then we also have the Chilas Comet. Chilas Comet is a very special development what we did there. As a laser physicist, most of the people say, hey, wait a sec, you've got these two rings, all these resonators there on the chip. You must have mode hopping there. Well, yes, there is a ton of mode hops there. We can mode hop free tune over a quarter of a nanometer. So if you want to tune over 50 nanometers, you have to stitch all those mode hop free tuning ranges nicely together. Thanks to the nice electronics we're having there, we can do that at warp speed. So within 1 second, we can sweep over 50 nanometers of tuning range. And there are some mode hops there, but they're indexed, and due to some analog control, give the handshake to the instrumentation when the laser is synced and when not. This goes very fast, because in a second you make a numerous of mode hops there, and 2% of the sweeping time, the laser is not synced in a mode hop, but the rest of the time, so 98% of the time, the laser is sweeping nicely. What you directly see is also one of the advantages here. After a sweep in time of the 1 second, it instantaneously goes to the start of the wavelength again. Since there are no mechanics involved in this laser, the laser can hit any wavelength within 10 milliseconds. So if you want to have a smiley on your oscilloscope, or you want to follow a set of absorption lines, but not all of the things, you can program the laser by a simple coding and go to subsections of the scan and scan over your absorption line, spectral lines you want to address. And the switching time is very fast, and that gives rise to some very nice applications. And especially, I think, for biomedical applications, we see there some niche things popping up. Well, here's a little bit of a video. Let me explain a little bit what we're looking at here. Here we took our Chilas Comet laser there, and we connected it to a wavelength meter. And this wavelength meter spits out the wavelengths over here and records the wavelength over time. What we don't see in the screen is that I'm touching some buttons on the background that I say to the laser, move a step up or move a step down in wavelength. So over here, I've got 8 picometers of step size. This laser is programmed with a grid of 8 picometers and scans throughout the full sequence. And you have to keep in mind, all these tricks also work for all the other wavelengths. What you see over here is that we make super tiny steps. You hardly see the digits changing nicely in 8 picometers. And we can repeat steps very accurately to the next step. You see a little bit of a wiggle here, and that's the tech controller inside the module that eases in and has to adapt for the new heater configuration. So you see a few, hundreds of a nanometer warp when settling to the wavelength. But you do see the instantaneously hopping to a new wavelength. So these are tiny steps, 8 picometer steps, and I can click to random wavelengths there. In the next slide, we increase the step size to 10 nanometers. So here's 10 nanometer steps, and we can directly go up and down. And you see over here, only this digit is changing, and the rest is more or less the same. The addressing from one wavelength to another wavelength is roughly with accuracy of 10 picometers. So that's roughly this digit or this digit. That's the accuracy we can achieve with these things. And again, with the analog input, you can also directly lock to any feature you want to go to. Now, obviously, we are showing here the Chilas Comet, and I will pause it again. Here we have the sweat mode there, and this instrument can monitor the wavelength with 2 kilohertz rep rate, so we can very fastly track the laser's wavelength. And yeah, upon start, you see that the laser is going to this programmed sequence of sweeping over 40 nanometers in this example. And it does it very smoothly. Now you have to remember that 2% of the time, the laser is not synchronized. So sometimes you see these errors popping up. Let me see if I can see it again. Repeat again. Sometimes you see an error on the screen, and that's related that the monitoring is not synchronized with the measurement. So sometimes the wavelength meter does not find a wavelength because the laser is in mode hopping mode. But that's only 2% of the time, and again, that is indexed by an analog input. You can trigger and synchronize your instrumentation to that. So this is the demo we have there. Here I demonstrate that we can also go to any subsection of scan. So I'll just click on the scan range I want to address. So you can increase, decrease, or go very fast to whatever feature you want to follow there. And I think it's nice to see that the agility of the laser is very fast. There's a Python library to integrate it to your setup. So you can directly plug in the coding there and use all the features we have available on the current devices. Well, what kind of applications do we see in the field? We've got one project running. It's a Dutch subsidy project. And in that project, we have the aim for making a swept source laser at 1064. Again, you need a little bit of project there. The chip runs are one of the main investments there. After we have the chips at hand, we can make a laser out of it and we can calibrate it to our setups, which we have here available. And then we partner up with a partner that can make gain sections around, emitting around 1064 nanometers. Well, what kind of applications do we aim for? Well, we aim for glucose analysis in the field. There's some blood analysis going on there. There is some features about bladder cancer treatment or scanning for these kind of things. And we've got this project going on now for almost 1 year. And we're aiming to have a laser around 1 micrometer available in Q1 2026. We will work together with CSC and Cardiff University and Wales, and we partner up with the ecosystems Chilas is enjoying here in Twente for the chip fabrication and for the assembly and integration of the laser and calibration. Chilas itself has a pilot assembly line, so new laser modules, batch verifications are always available, so we can do our own integration as well. And after we have a product and the volumes go up, we can go across the street to fix photonic assembly and there scale up the production easily. This is another very interesting feature. It's one customer, they do photoacoustic imaging. In this setup, they have a laser pulse that shoots light into your tissue, and you get absorption depending if you hit the lipids or other components in your skin or in your tissue. And you get an acoustical wave being generated on the pulse, repetitive pulse of the impinging laser. Now here it's of importance to collect the acoustical waves with an ultrasound detector. I think in most of the cases right now they've got an array of acoustical sensors. Well, in this application we changed the ultrasound detection by an optical interface, and basically they need to have a laser pointing at several spots on the surface while monitoring the acoustical waves coming out of this tissue. And therefore they employ a Chilas laser because it can hit any wavelength they want to hit within a few milliseconds, stay there for a while, record the acoustics, and then go to another spot where the wavelength might be different, and then do the same trick there over again. So they have to scan an array of points within a fraction of a second, and therefore they employ the Chilas laser. They're building this into their machine right now, and hopefully we get handheld devices for this photoacoustic imaging device on the market soon. Now, if you look at the laser, we have a huge traction at the OCT applications. OCT is a technique where you scan the wavelength range, and from the reflected light, you can then trace back at which depth you have what kind of tissue there. So it's a topology / in-depth information you get there. So I think it's the acoustical version of the echoscopy. Now, for these scans, typically they have used instruments, like you see on the picture, and very fast scanning lasers. Well, the Chilas lasers can scan very broad wavelength range. That's no problem for these scans, but for OCT, the scan rate of 1 second per scan is too slow to drive the current OCT applications. We're developing new technology to speed that up, but that's not available yet. But for now, what I find in the OCT applications is the so-called full view OCT applications, where they blow up the beam of the light over a full CCD area and then make a confocal projection back on the CCD area while scanning the laser with 1 second. And then you get all the depth information into 2D within 1 second. And I think that will be an application for the Chilas laser to be popping up. You have to remember that the line width of the Chilas laser is only 1 kilohertz, about 1 kilohertz. This means that the coherence length of the laser, so that wave, the optical waves are interacting with each other in a coherent way, extends to up to 10 kilometers. And this brings OCT to the next level. So you can get some very high resolution information, very long distances, by building up an interferometer of the reflected light combined with the send out light. And this is something we are currently developing together with partners in Germany. Then there are numerous of applications in the biomedical fields relying on spectroscopic analysis. And you have to correct me if I'm wrong, but there's, for example, fluorescent biomarker detection or imaging. There's absorption for gas analyzers, or also in vivo, there are some absorption lines which give you some markers of material which is available there. There's Raman spectroscopy going on. There's microscopy going on there, and there's flow cytometry going on. And there's a lot, there are too many applications where the laser could fit in. Typically what we want there to build up together with the customer is what wavelength do you need for your application, what can we make there, and what resolution you need to address. Raman can be very fine. You might have stimulated Raman going on where you need 2 lasers at some specific wavelengths. And these are all things that can be made by Chilas. Then looking at the audience we're having here, I think there's numbers of people outside the biomedical applications there. And this is another a project, Adequate project. In this project, we developed a laser for an on-chip cold atom internal sensor. But actually, I had 2 lasers. One laser emitting at red lights for trapping the atoms there, and there is another laser we developed there, which is at around 1560 for locking to that transition, atom transition there, for optical sensing. Well, what can you do with these sensors? And I think this is the fun thing about making very specialized lasers, is they can make sensors that can measure gravitational fields. And the ultimate goal is obviously to get rid of the current GPS system, but just use the gravitational field of the moon, the sun, and the earth to know where your orientation is. Well, these sensors are so sensitive that if you put these atomic clocks into an elevator and you go from ground level to the 40th floor, the clocks will start to tick in a different manner. Hence, you measure the gravitational field. And this is all according to the rules of Einstein. So not too novel in theory, but to measure these kind of effects, you need very, very specialized lasers. The current line of lasers used in these applications do not fit in my office, and they're very large, but thanks to integrated optics and the stability we see inside these chip-based lasers, we can now dream about having lasers in space that can do these measurements. Another big thing we pop up, especially for Europe, since we are full production in Europe, is quantum key distribution. This is a way of quantum encryption of data. Here you have to think about that quantum states are sent over the current existing telecom networks in the field. And for doing that, you need a very narrow line width and a stabilized laser. So there we develop a stabilized laser for driving quantum key distribution networks in Europe, but also we get traction of satellite communication, where they do the same trick, but then free space. Well, you can imagine that if you want to put something into a satellite, the laser has to be very light and compact. Well, here Chilas offers a very nice solution that can be shoot into air. We've got a project developing our lasers for that. That is the Quarter project. And there we have developed a stabilized laser. And you see here a little bit of the interior of the box. It's not too hard to make. Well, the development takes a bit longer, but it's a very simple thing. And here what we aim for is we have a stabilized circuit, an additional circuit onto the chip that we can lock the laser to, so we get very, very low drifts and low wavelength variations while operating the laser. And this is for quantum key distribution networks of essential to drive these systems. Got a big group of people working together there, and we will launching the product there, I think, in 2026. There's a little bit of looking out what else you can do. I was looking for biomedical applications here, and within the Twente area there are many more applications going on there, many more companies making lasers on chip or other things there. Well, this is an example of Brilliance RGB. What these guys do, they actually make 3 lasers on a single chip. You see them sitting over here. There's red, green, and blue. Perhaps the other way around, I don't know exactly. And they sit on a very tiny tile here. I think the thing is something around 2 millimeters by 2 millimeters. And the nice thing what this thing does is that it combines red, green, and blue light into a single emitter to the output. And this is what you need for projection of light in a beamer like. Well, this is a very small beamer light engine for your projection, and this is typically used for integration into your glasses, like a Google Glass we might know, and it helps, for example, in the medical industry to aid the surgeries, to be augmented reality, virtual reality, to do some actions onto the human body or the tissue to help them integrating the diagnostics that's done in vivo. Good, I think this is my last slide, and I would like to open the audience to have some questions about this. Thanks for your attention.